Well, hello everyone, and welcome to this very short video where I show you one of the things I've been toying with, which is the question of how do I order a number of vertices so that they form a polygon all the time when I draw a line between each of them in the order in which they are sorted. So let's have a look here. I have these 6 points, these 6 cubes, and I draw a polygon based on their position here. And if I move this one around, well, the order in which the lines are drawn is changed according to its position. And yeah, it was a little bit of an adventure to figure out how to do it because I'm really not great at geometry. So let's see what if I go really far, like this changes the order as well of the others. So let's see. First, I'm going to explain at a high level what's going on. So I take all the positions here, position vectors, and I do the average of their positions. So I sum them all up and I divide it by the number of vectors, which gives me this center point here. That's going to be that is the geometrical center of my my polygon. And then what I do, as you can see, there's lines here. Those are vectors that I compare to the forward vector of the center, and I look at the angle between the forward vector of the center and the direction to each vertex. And by sorting the vertices according to their angle, I get the correct order, and then I can draw this. So let's look at this in code. I have this sort as polygon that takes as a reference an array of vector 3 points. And I calculate the center, so I do the sum of all points and then divide by the number of points. And then I sort the array using a comparison function that I define, and that is clockwise compare, and it compares two points in the array of vector with the center, with their angle to the center. And according to that, so the clockwise compare will project first all the points on the same plane, otherwise this will not work. And then I position point 1 and point 2 relative to the pivot point, so that the pivot is the origin in that local space of the comparison function. And then I just calculate the difference between the signed angle of the forward vector of the compared to the origin, which is our pivot, and the point according to an up axis. So why do I use a signed angle? The difference between signed angle and normal angle is that the normal angle will calculate the shortest angle. So if I look here, for example, the angle between the forward vector here of the center point and this is going to be like 5 degrees or something. But the angle between this up vector and this here will not be, it's not a clockwise angle. It's the shortest angle. And so that's a bit of a problem, because these two, if I put them like in such a way that, let's put them both at a 45 degree angle, something like this. So if I put them both like this, well, they both have an angle of 22.5 degrees compared to the forward vector. So they're equal, which is not what we want. We want them to be different. We want that to be a smaller value than this. And that's why I use the signed angle, because the signed angle takes an axis of rotation, and it allows me to say, if you have to rotate counterclockwise, then the resulting angle will be negative. And if you have to rotate clockwise, then the resulting angle will be positive. And so that sorts this problem. That's why I use signed angle. And so I do the difference, and then I do a couple of shenanigans here to get a sealed value, because I need to compare. So the comparator needs to return an int. And if I just round the resulting integer, well, if I have angles that are close, like really close, they will end up being equal, which is not what I want. I really want, even if the difference is very small, if essentially it's when the difference is less than 1 degree, which will not happen most of the time, but it could. And I really don't want that to happen. So I do a bit of shenanigans here. I take the absolute value that I multiplied with the sign. I take the absolute value that then I seal to the smallest integer greater to this. So if it's an angle of 0.1, then the result will be 1. And if it's an angle of minus 0.1, that's why I take the absolute value, because if I didn't take the absolute value, then the result would be 0. So I take the absolute value, so the result is 1, and then I sign it, so it becomes minus 1. So an angle of minus 0.1 will be an angle of 1. And so that's the way I kind of make sure those edge cases work. And then I just draw a polygon here, taking all the vectors and drawing a line from one vector to the other. And then finally, I do modulo points.length, so that I also draw from the last line from the last one to the first one. And that's what gives us this. The reason why I do this, well, is because, back to the pathfinding thing, I want to be able to know if a specific point is inside the domain of vectors that of the velocity obstacle. And so for that, I need to be able to order these things in the right order, because in order to know if a point is inside a polygon, well, you have to see if the point is on the right or on the left of all the lines that are drawn. So if they're drawn clockwise, then it has to be on the right of the line. And if they're drawn counterclockwise, it has to be on the left of all the lines. And there's a mathematical function to figure that out rather simply. That's why I had to put them in the right order. Otherwise, I wouldn't be sure that it's on the right at all times. So anyways, that was it. Hope it served some purpose. I don't know. But I'm having fun doing this anyways. So that's it. Checking out, and see you on the next video.